In today's lesson, we are going to learn about zeros and how many there are. So it's important to remember that our zeros is where y equals 0, and that happens on the x-intercept. Anything that's on the x-axis means it has a y value of 0. So before we continue, it's really important that you take the time to pause this video and graph the following function. You're going to need it in order to follow along with the rest of the lesson. So hit pause, graph it. There's two ways, remember. There's table of values, it takes you a little bit longer, and there's also graphing by transformations. Whatever you prefer, and then join back in when you're done. If you've done the graph correctly, you will get the following here. You can see that you have a vertex at +5, +5 and -2, and your graph opens up because your A value was +1. So our question in question A says, how many zeros does f at x have? So a 0 happens anywhere where it's touching the x-axis. So there's a 0 there and a 0 there. In both of those places, the x value is about, let's say 3.5 there and about 6.5, but both the y values are 0, hence the term are zeros. If something happens that your graph doesn't look exactly like the one that's followed, take the time to pause the video, figure out where you went wrong, and make any corrections. Because being able to graph, especially graphing by transformations, is so important because it reoccurs throughout the whole entire course. Now that we've done question A, how many zeros there are, we deem that there are 2 zeros. Our next question for B is as follows. Suppose we just wanted to visualize the graph instead of actually graphing it. What are the important aspects of the graph that would help us determine the number of zeros? So the two things that are so important to us is the direction of opening, whether the graph opens up or down, and your vertical translation. That means whether it has moved up or down at all. Because say we had this graph here and the graph opened down, we no longer have any zeros. This graph continues forever in the negatives of the y, and so the vertex won't change there. It doesn't increase, so there are no zeros in that example. So we'll clean that up. So the direction of opening is so important, and how much up or down it has moved. So determining the number of zeros without graphing revolves around two things. Your A value, whether it is positive or negative, because that's what tells you if it opens up or down. And the other thing that's so important is our Q value, because that tells us how much up or down we've translated our graph. So good things to get into your notes there. Let's do a few examples together here. We'll make some space, do a few examples together of these questions where we don't graph to find out how many zeros there are. We can just do it by sketching. Keep in mind this works for how many zeros there are, not if it's asking you what the zeros are. So in our first example here, I'm just going to make a quick grid for a sketch, and I know that my graph opens down because that's -2, and it has a vertex at -1. I'm going to make this a little bit longer here, and -3. So I have a vertex there, and I know that my graph opens down. So I can see from my first example, there are no zeros that are going to happen, no intercepts. So it's pretty quick when you can sketch. Let's look at our second example here. Again, it opens down because that is -3, and I have a vertex at +5 and +1. And your graph can be as rough as mine is here. Doesn't have to be accurate, just as long as you can see the vertex and the direction of opening. So here, we know that we are going to have 2 zeros. There's 2 places where the graph touches the x-axis. Our last example, I know that my graph's going to open up because that's +2, and I have a vertex of 5 and 0. So my vertex happens right there on the x-axis and opens up. So as in that example, when my graph doesn't move up or down at all, I can see that I have 1 0. Those are the only 3 cases that can occur. You're going to either have no zeros, 1 0, or 2 zeros. Now this method is perfect when we're in vertex form, but what happens when we're in standard form? Like it represents here, remembering that standard form is ax squared plus bx plus c. Then what do we do? Let's start with a quick example of f of x equals 2x squared plus 5x minus 3. The easiest thing to do, keep in mind, is to first see whether you can factor it. Because if you can find out what the zeros are right away, and that will answer the question of how many there are. We can also do the quadratic formula. So I'm first going to see if there's any way of being able to factor this. So 2 times negative 3, a times c equals negative 6, and my b is positive 5. So positive 6 times negative 1 would work. So if I factor it, 2x squared plus 6x minus 1x minus 3. I have my magic numbers. We're also reviewing decomposition here. And then I can factor by grouping. 2x, x plus 3, factor out negative 1, and I'm left with x plus 3. For a final answer of 2x minus 1 and x plus 3. So I know that my zeros, my first one happens at positive 1/2, and my second one will be at negative 3. Therefore, answering the question that is asked, there are 2 zeros. Let's look at another question in standard form where we can't do it just by sketching. We have 4x squared minus 2x plus 7. We try to see whether we can factor it by decomposition. 4 times 7 is 28. But there aren't any combinations that would equal, that I can think of off the top of my head, that would equal to be negative 2. Make some space here. So we have to remember that we can find our zeros, what they are, by doing the quadratic formula. So we get minus b plus or minus the square root of b squared minus 4ac all over 2a. Now oftentimes, because of this plus or minus, and remember from past lessons, we're going to end up with 2 zeros. But it might not always happen. Take the time to sort of reflect what would happen how would we know if there was only 1 0 or no zeros at all? Alright, so let's continue with this question. We're going to quickly substitute in. So we're going to have positive 2 there, because I substituted in negative 2, plus or minus negative 2 squared. Then we're going to do 4 times 4 times 7. All over 2 times 4. So here we have 2 plus or minus 4 minus 112 all over 8. Well, I can quickly see right here, this is going to give me a negative number under the square root. And we have to keep in mind that we can't square root any negative number. There's no solution. So immediately here, this is how we can tell whether there's any roots or not. There's not going to be in this example. So really, the only part that's really important to find out how many zeros there are, if we don't need the exact value, is just this b squared minus 4ac. And this actually has a term, an actual name. It's called a discriminant. Another thing that's important for your notes. So before you get into the quadratic formula, we can use this discriminant to find out how many zeros there are. So have a look. That's what we have here is our discriminant, and how we can tell if there's solutions or not. You can see that if our discriminant is less than 0, meaning that it's negative, there's no solutions. There's no roots that would work. If our discriminant equals exactly 0, then that means there's one real root. And if our discriminant is greater than 0, there are 2 roots. And there it is there, our discriminant. A good thing to have in your notes. So our last thing we need to do today is we've talked about vertex form and that we can sketch. We've talked about standard form and we can use the discriminant. Now we just have to remember, a little bit about intercept form or factored form. Now our intercept or factored form tells us our intercepts. And we can tell here that these are intercepts because both our y values are 0. So if we're given intercepts and another point on our graph, we can actually write a quadratic equation just with that information. So the first thing that we would do is remember that our function is y equals a x minus s, our first intercept, and x minus t. So I'm going to leave the y for now, and the a, I don't know what my a value is, and I'm going to substitute in my intercepts. So I practically have a perfect quadratic equation, but I don't know what a is. This last point that's on the parabola will help us out, because we know that the -3 is an x value, and the +2 is a y. So before I go any further, let's just clean this up a bit. So I'm going to substitute my y into my y value. It's easy to confuse. Be sure the 2 goes into y. The 2 goes into y. Again, fix that a. And that my -3 is the x value, and it goes in anywhere where there's an x. Then we can just isolate, and solve for a. -8 multiplied by -6, which is +48. So if we divide this side by the same thing, and this side by the same thing, we are left, if we reduce, with a final answer of 1/24. Now, just remember, to be sure, it wanted to know what the equation was, so we want to finish and actually write the equation out. 1/24 x minus 5 and x minus 2. That's the final equation in intercept form. If you wanted it in standard form, you would just expand and gather like terms. I'm going to leave you with this last example here. When you're dealing with radicals, keep in mind it wants the exact value. So don't simplify. So we're combining our day 1, our last unit, and all of this all in together. So try this question, bring in everything that you have to class tomorrow, and we'll discuss it at the beginning.